Vacuum revolution. The concept of the vacuum has fascinated, perplexed, and challenged human civilization for millennia, long before it became the foundational enabling technology of the modern electronic era. The vacuum was merely a philosophical abstraction, a subject of intense debate among ancient scholars. In antiquity, around the 5th century BCE, the ancient Greek philosopher Democritus proposed a radical theory that the universe consisted entirely of tiny, indivisible particles called atoms, and that the vast expanses between these particles were composed of absolutely nothing. This notion of a space entirely devoid of matter, a perfect vacuum, was deeply controversial. It was famously rejected by Aristotle, who posited that nature inherently abhors a vacuum, arguing that empty space was a physical impossibility because the surrounding matter would immediately rush in to fill it. For nearly 2,000 years, the Aristotelian paradigm dominated scientific thought, effectively stalling empirical investigations into the nature of empty space. The word vacuum itself, derived directly from the Latin word vacuus, meaning empty, remained largely theoretical until the scientific awakenings of the 17th century. It was not until 1649 that the theoretical became tangible. Otto von Guericke, a German physicist and the mayor of Magdeburg, invented the world's first mechanical vacuum air pump. With his rudimentary brass pump, von Guericke was able to suck the air out of two hollow copper hemispheres, demonstrating to astonished crowds that even teams of horses could not pull them apart against the crushing weight of the outside atmospheric pressure. This dramatic demonstration proved the physical reality of the vacuum and the immense invisible power of the ocean of air that surrounds us. However, while von Guericke had proven that a vacuum could be created, it would take another 2.5 centuries for the true potential of vacuum technology to be fully realized, refined, and harnessed for industrial and scientific applications. The journey from von Guericke's hand-cranked brass cylinders to the highly sophisticated, industrially scaled vacuum systems that powered the mid-20th century represents a profound technological paradigm shift. It is a sweeping narrative of breaking fundamental mechanical limits, mastering the counterintuitive physics of highly rarefied gases, and translating delicate laboratory curiosities into mass-produced industrial miracles. From the late 19th century through the catastrophic global conflict of the Second World War, the progressive refinement of vacuum technology directly precipitated a series of cascading technological revolutions. Without the ability to evacuate glass envelopes to infinitesimally low pressures, the discovery of subatomic particles would have been physically impossible. Without the mastery of thermionic emission in a vacuum, the entire fields of global telecommunications, radio broadcasting, and television would never have materialized. Furthermore, the immense and unparalleled wartime mobilization of the 1940s relied unequivocally on sophisticated vacuum systems to develop microwave radar, deadly proximity fuses, enriched uranium for atomic weaponry, and the world's first electronic digital computers. This exhaustive research report traces the granular evolution of vacuum technology and its monumental applications, examining the mechanical breakthroughs, the theoretical physics of molecular flow, the rigorous manufacturing processes, and the historical milestones that definitively shaped the trajectory of the 19th and 20th centuries. Late 19th century breakthroughs. During the latter half of the 19th century, the pursuit of scientific knowledge regarding the nature of electricity and gases was fundamentally bottlenecked by the severe limitations of existing vacuum pumps. Piston-driven mechanical pumps, which operated much like a reverse bicycle pump, were useful for basic demonstrations, but were entirely incapable of achieving the high vacuum levels required to study the behavior of electrical discharges in rarefied environments. The mechanical seals simply could not prevent microscopic amounts of air from leaking back into the chamber, and the pumps could only draw out so much air before the internal pressure dropped too low to push the exhaust valves open. The critical breakthrough that shattered this limitation arrived in 1865, when a Hanover-born chemist named Hermann Sprengel, working in London, invented the Sprengel pump. Abandoning the use of mechanical pistons, levers, and valves, Sprengel devised an elegantly simple and ingenious system that utilized the fluid dynamics of falling liquid metal. The Sprengel pump operated by allowing individual drops of elemental mercury to fall continuously through a small-bore glass capillary tube. As each heavy drop of mercury descended through the narrow glass passage, it effectively acted as a liquid airtight piston. The falling drop trapped a microscopic pocket of air from the system being evacuated, carrying it down the length of the tube and forcing it out of the exhaust at the bottom. Because mercury is incredibly dense and possesses a relatively low vapor pressure at room temperature, the pump could draw air out of a sealed glass vessel with unprecedented, albeit slow, efficiency. Within 20 minutes of operation, a standard 1-liter glass bottle could be essentially emptied of all atmospheric air, achieving an internal pressure as incredibly low as 1/1,000,000th of standard atmospheric pressure at sea level. This vacuum level, less than 1 micropascal, represented the highest vacuum achievable in the world at that time and opened the door to an entirely new realm of physics. The impact of the Sprengel pump on the trajectory of 19th century science simply cannot be overstated. By providing a reliable tool that could practically eliminate the interference of atmospheric gas molecules, the pump directly enabled what historians often refer to as the second scientific revolution. Researchers equipped with banks of Sprengel pumps and specialized glass vessels known as Geissler and Crookes tubes began conducting strange and beautiful experiments passing high-voltage electrical discharges through highly evacuated spaces. English physicist William Crookes famously utilized Sprengel pumps connected in series to achieve the extreme vacuums necessary for his studies of these mysterious electric discharges. In a deep vacuum, these discharges appeared as glowing, straight beams of light traveling from the negative electrode, the cathode, to the positive electrode, the anode. These cathode rays quickly became the subject of intense international scientific scrutiny. Because the vacuum was deep enough to prevent residual gas ionization from masking the delicate results, scientists finally isolated and manipulated the pure rays themselves. This led directly to two of the most important discoveries in the history of physics. In November 1895, at the University of Würzburg in Germany, the German experimental physicist Wilhelm Röntgen was operating a highly evacuated cathode ray tube in a darkened laboratory. He had covered the tube in heavy black cardboard, yet he noticed that a chemically coated fluorescent screen sitting across the room unexpectedly began to glow. He had discovered X-rays, a completely new, invisible form of highly penetrating electromagnetic radiation produced by the impact of cathode rays on the glass walls and metal anodes of the vacuum tube. Just months later, in 1896, the French physicist Henri Becquerel accidentally discovered natural radioactivity while investigating a suspected relationship between the fluorescence of certain uranium minerals and Röntgen's newly discovered X-rays. The most fundamental consequence of this high vacuum experimentation, however, occurred in 1897. The British physicist Joseph John Thomson, utilizing highly exhausted vacuum tubes, decided to subject these mysterious cathode rays to both magnetic and electric fields. Because the vacuum was deep enough to prevent residual gas ionization from masking the delicate results, Thomson successfully deflected the glowing beams and measured their properties. He proved conclusively that the rays were not waves of light, but were actually composed of streams of negatively charged particles that were significantly smaller and lighter than any known atom. He had discovered the electron, the very first subatomic particle ever identified. This monumental discovery permanently dismantled the ancient Democritean notion that the atom was a solid, indivisible sphere. The discovery of the electron fundamentally altered human understanding of matter, revealed the electrical nature of the atom, and laid the theoretical groundwork for the entire subsequent field of electronics, an achievement completely reliant on the mechanical elegance of the Sprengel mercury dropping pump. The illumination and valve revolution. While physicists in university laboratories utilized high vacuums to probe the fundamental invisible nature of the universe, practical inventors and engineers rapidly recognized the immense commercial and industrial potential of space devoid of matter. The most immediate and globally transformative application of vacuum technology was the development of practical incandescent electric lighting. For decades throughout the 19th century, inventors had attempted to create electric lights by passing strong electrical currents through highly resistive filaments, causing them to glow with heat. However, these materials inevitably combusted and burned away almost instantly when exposed to the oxygen in the atmosphere. The obvious solution required encasing the filament in a sealed glass bulb and removing the air. But early mechanical piston pumps could not achieve a deep enough vacuum to prevent rapid oxidation, leading to blackened bulbs and quick filament burnout. It was the Sprengel pump that finally breached this commercial barrier. In 1879, working independently of one another across the Atlantic, inventors Thomas Alva Edison in the United States and Joseph Swan in the United Kingdom realized that the extreme vacuum provided by a modified mercury dropping pump would allow a fragile carbonized filament to glow brightly for hundreds, if not thousands of hours without deteriorating. Edison utilized a heavily modified mercury drop pump to systematically exhaust the air from his experimental bulbs, eventually reaching a pressure of less than 1/1000th of a torr. This specific deep vacuum threshold was absolutely necessary to allow for the chemical gettering of residual water vapor and the complete prevention of filament combustion. The successful commercialization of the incandescent light bulb not only illuminated the streets and homes of the world, but also drove the very first massive global industrial demand for vacuum technology. It forcefully transitioned the vacuum pump from a bespoke, handcrafted laboratory instrument into a rugged cornerstone of mass industrial manufacturing, setting the stage for the electronics industry. As Edison worked tirelessly to perfect his incandescent bulbs and extend their lifespans in 1883, he observed a peculiar and troublesome phenomenon. The inside of the glass envelopes progressively darkened with a black soot over time, obscuring the light. In an attempt to investigate the cause of this blackening, Edison inserted an additional separate metal electrode plate into the glass bulb, completely unconnected to the glowing filament. He discovered a baffling effect. If he connected this extra electrode plate to the positive side of the heated filament's battery, a small electrical current would inexplicably flow through the completely empty vacuum space from the hot filament to the cold plate. However, if the cold plate was connected to the negative side of the battery, absolutely no current flowed. Edison had inadvertently observed thermionic emission, the physical process where thermal energy causes electrons to literally boil off the surface of a heated metal and fly into the surrounding vacuum. Lacking a practical, immediate commercial application for this strange unidirectional current flow, Edison simply patented the observation, which became known as the Edison effect, but largely abandoned its deep scientific study. The true world-changing potential of the Edison effect was finally realized 20 years later by the brilliant British physicist John Ambrose Fleming. Serving as a scientific consultant to Guglielmo Marconi, the legendary pioneer of wireless telegraphy, Fleming was acutely aware of the severe limitations of early radio receiving equipment. The magnetic detectors and rudimentary coherers of the time were highly erratic, fragile, and insensitive, struggling to reliably detect the faint high-frequency alternating currents generated by distant radio waves. In 1904, Fleming recalled the Edison effect bulbs he had seen years prior and recognized a profound application. Because the one-way flow of electrons in a vacuum acts as a perfect electrical one-way street, the device could act as a perfect rectifier. It could convert the rapidly oscillating high-frequency alternating current of a captured radio signal into a smooth, direct current capable of driving a measuring meter or a telephone earpiece. Fleming constructed a specialized two-element vacuum tube consisting solely of a heated cathode to emit electrons and a cold metal anode plate to catch them, which he officially named the oscillation valve. The Fleming valve, recognized today as the world's first practical thermionic diode, proved to be a highly reliable, sensitive radio detector and officially marked the dawn of the electronic age. The evolution of the vacuum tube accelerated at a blistering pace thereafter. In 1906, the ambitious American inventor Lee DeForest sought to improve upon Fleming's diode design to create a more sensitive radio receiver. DeForest introduced a crucial, revolutionary third element into the vacuum envelope, a delicate zigzag wire structure, which he called a grid, positioned directly in the empty space between the heated filament and the positively charged anode plate. DeForest named this three-element vacuum tube the Audion. While initially utilized merely as a more sensitive radio detector, the Audion's true world-altering capability was uncovered a few years later in 1912 when it was successfully utilized as an electronic amplifier. By applying a very small, fluctuating electrical signal, such as a faint, distant radio wave picked up by a wire antenna to the grid, DeForest found he could exert immense precise control over the massive flow of electrons streaming from the hot filament to the plate. The grid acted exactly like an electrostatic gate or a Venetian blind. A slight negative electrical charge applied to the grid would aggressively repel the negatively charged electrons back toward the filament, severely decreasing the current reaching the plate. Conversely, if a slight positive charge on the grid would accelerate the electrons through the wires toward the plate, massively increasing the current. This unprecedented ability to take a weak, almost imperceptible signal and replicate its exact waveform at a much higher power level fundamentally transformed the landscape of global telecommunications. The Audion triode allowed for the cascading amplification of audio signals, directly enabling the construction of long-distance transcontinental telephone lines, and made the continuous wave transmission of the complex human voice via radio a practical reality, finally moving the world past the era of staccato, static-filled Morse code sparks. Predictably, the immense commercial and strategic magnitude of this invention sparked decades of fierce, highly disruptive patent litigation that shaped the early electronics industry. The Marconi Company, firmly holding the rights to Fleming's original diode patent, aggressively sued DeForest for patent infringement, arguing legally that the Audion was merely a derivative modification of the original oscillation valve. This bitter, expensive legal impasse stifled rapid commercial integration until the desperate demands of World War I forced the government to intervene and mandate cooperation. The complex litigation dragged on through the courts for decades until 1943, when the United States Supreme Court finally ruled that Fleming's original patent was actually invalid due to prior art by other scientists, a posthumous and highly complex legal victory that underscored the immense financial, corporate, and strategic value of vacuum technology in the 20th century. Breaking the mechanical limit. As the global consumer demand for incandescent lamps, medical X-ray tubes, and thermionic radio valves skyrocketed in the early decades of the 20th century, the foundational technology used to manufacture them, the reliable but ancient Sprengel pump, became a critical, strangling bottleneck. While the mercury drop pump could theoretically achieve excellent ultimate vacuums given enough time, its volumetric pumping speed was agonizingly slow, often requiring many hours to completely exhaust a single glass envelope. The vision of industrial mass production of electronics required a complete paradigm shift in the mechanisms of vacuum generation, moving definitively away from slow, gravity-fed droplets toward high-speed, continuous, high-volume evacuation. This monumental engineering challenge was met and conquered by the brilliant theoretical insights and mechanical inventions of two giants in the field of physics and chemistry, Wolfgang Gaede in Germany and Irving Langmuir in the United States. The transition to molecular flow physics. To truly understand the revolution that occurred in vacuum technology in the 1910s, one must first understand the distinctly different physical regimes that gases exhibit under decreasing pressure. In the everyday world and in the early stages of evacuating a chamber, gas exists in a state known as viscous flow. At near atmospheric pressures, billions of gas molecules are densely packed together and collide with one another far more frequently than they collide with the walls of their containment vessel. The average distance one molecule travels before violently striking another, a metric known as the mean free path, is exceedingly short, often fractions of a millimeter. Under these crowded conditions, the gas acts very much like a continuous, cohesive fluid, exhibiting internal friction and measurable viscosity. Pumping gas in the viscous flow regime relies on standard Newtonian mechanics and fluid dynamics. A mechanical roughing pump, using spinning vanes or pistons, physically sweeps the interconnected mass of gas out of the chamber, much like a snowplow pushing a drift of snow or a water pump pushing water through a pipe. The gas moves collectively because the molecules are constantly bumping into one another, transferring the pushing force throughout the volume of the gas. However, as the mechanical pump removes more and more air and the internal pressure drops significantly below 1 millibar, the gas undergoes a profound and highly counterintuitive behavioral shift, entering the regime of free molecular flow. In this extreme state, the vacuum chamber has been emptied of so much physical matter that the remaining gas molecules are vastly separated from one another. The mean free path of the molecules becomes incredibly long, eventually becoming longer than the physical diameter of the vacuum chamber itself. To use an analogy, viscous flow is like trying to run through a densely packed concert crowd, where every movement pushes against dozens of other people. Molecular flow is like placing 3 blindfolded people inside a massive, empty gymnasium. They will almost never bump into each other. Instead, they travel in perfectly straight lines until they accidentally strike the walls of the room, bouncing around entirely at random. Because the gas molecules no longer interact with or collide with each other, they completely lose their fluid characteristics. They cannot be pushed or pulled as a cohesive mass. Standard mechanical pumps, which rely on creating a pressure differential to suck air out, become entirely useless in the molecular flow regime. If a molecule wanders into the mouth of a mechanical pump, it might bounce back out before the mechanical valve can close. Removing these highly rarefied, randomly wandering gas molecules requires an entirely different approach: momentum transfer. The pump must physically strike the individual wandering gas molecules with something faster and heavier, imparting a strong directional velocity to drive them forcefully toward the exhaust pipe before they can bounce back into the clean chamber. Gaede, Langmuir, and the diffusion pump. Wolfgang Gaede, a brilliant and highly prolific German physicist who would eventually hold nearly 40 vacuum-related patents, deeply recognized the hard limitations of mechanical suction in the molecular flow regime. Gaede originally studied medicine before switching to physics, and his early frustration with the agonizing slowness of the Sprengel pump drove his career. In 1909, Gaede invented the world's first molecular drag pump, which cleverly utilized a rapidly rotating metal cylinder to impart momentum to gas molecules through sheer physical friction, literally dragging the randomly bouncing gas molecules along the wall of the pump toward the exhaust. While theoretically sound and capable of reaching high vacuums, The molecular drag pump required incredibly tight mechanical tolerances between the spinning rotor and the housing, making it highly prone to catastrophic mechanical failure and expensive to manufacture. Gaede's true masterpiece, which changed the world forever, arrived in 1915 with his invention of the diffusion pump. Gaede aggressively challenged the prevailing scientific belief of the era, which stated that a mercury-based pump could never achieve a vacuum pressure lower than the ambient vapor pressure of the elemental mercury itself. He hypothesized that if wandering gas molecules could be forced to diffuse into a rapidly moving, continuous stream of heavy vapor, they could be swept away continuously without any moving mechanical parts. Gaede's original prototype pump involved boiling a pool of elemental mercury at the base of the pump to create a high-velocity, upward-moving vapor stream. This hot vapor was directed to flow past a narrow set of mechanical slits connected to the vacuum chamber being evacuated. As the highly rarefied air molecules bounced randomly around the vacuum chamber, pure chance would dictate that some would wander into the narrow slits and diffuse across the boundary into the roaring stream of mercury vapor. Because the heavy mercury atoms were traveling at incredibly high speeds in a single direction, they would violently strike the lighter air molecules, transferring massive momentum and carrying them rapidly toward the air-cooled condenser region of the pump. Upon hitting the cold walls, the mercury vapor would instantly condense back into a liquid and drip down to the boiler to be reused, while the trapped air molecules were pushed into a roughing pump and expelled into the atmosphere. Gaede officially named his elegant invention the diffusion pump, emphasizing his theoretical stance that the gas cannot physically diffuse backwards against the massive momentum of the vapor stream. Simultaneously, across the Atlantic Ocean, the brilliant American chemist and physicist Irving Langmuir, who would later win a Nobel Prize for his work in surface chemistry, read Gaede's published academic papers on the diffusion pump and immediately identified a way to radically optimize and scale the design for massive industrial use. Langmuir argued that the primary, most effective physical mechanism at play was not merely gas diffusion, but rather condensation. In 1916, Langmuir introduced his revolutionary umbrella design, which entirely abandoned Gaede's restrictive, narrow diffusion slits. Instead, Langmuir designed a system that directed a massive, high-speed blast of boiling mercury vapor upwards through a central chimney, where it hit an umbrella-shaped deflector that forced the vapor to blast fiercely downwards, forming a wide, conical curtain of vapor directed toward the outer water-cooled walls of the pump. This downward-facing vapor jet acted exactly like a modern high-powered garden leaf blower moving scattered leaves. It violently and efficiently entrained the randomly bouncing air molecules that drifted into the top of the pump, blasting them relentlessly toward the bottom exhaust. Langmuir's brilliant aerodynamic modifications resulted in volumetric pumping speeds that were phenomenally fast, operating seamlessly from low pressures all the way down to the extreme high vacuum range required by the latest electronics. The diffusion pump represented a perfectly elegant, moving part-free solution to achieving deep high vacuums at a massive industrial scale. However, the early heavy reliance on boiling elemental mercury as a working fluid posed severe toxicity hazards to factory workers and required the mandatory use of expensive, cumbersome liquid nitrogen cold traps to freeze the mercury and prevent its stray vapor from backstreaming into the clean vacuum chamber and ruining the electronic components. This critical limitation was beautifully overcome in the late 1920s when researchers C.R. Birch in 1928 and Kenneth Hickman in 1929 successfully developed highly refined synthetic hydrocarbon and silicone oils, which possessed exceptionally low vapor pressures even at room temperature. Oil diffusion pumps rapidly became the ubiquitous, unquestioned standard across the globe, forever breaking the mechanical limits of vacuum generation and paving the way for the mass production of complex, reliable electronics. Because the diffusion pump has no spinning blades or tight mechanical tolerances, its physical pump throat could be manufactured to massive dimensions, yielding an unparalleled capacity for capturing randomly wandering molecules. In the physics of molecular flow, the primary factor determining how fast you can pump a chamber is simply the size of the hole the molecules can wander into. While later highly advanced mechanical turbomolecular pumps were strictly limited by the physics of spinning rotor blades to inlet flanges of around 250 millimeters, 10 inches, a diffusion pump could be built with a massive 1 meter inlet diameter. Because the area of a circle increases with the square of the radius, a 1 meter diffusion pump offers a flow area 16 times larger than a 250 millimeter pump, easily achieving a staggering pumping speed of 50,000 liters per second. The science of getters and industrial manufacturing. The advent of the high-speed oil-based diffusion pump entirely revolutionized the manufacturing of vacuum tubes, transforming them practically overnight from artisanal, hand-blown laboratory creations into mass-produced industrial commodities. As massive companies geared up for the global radio boom of the 1920s and 1930s, the physical process of exhausting tubes was highly automated on rotating assembly lines, but the deep physics of maintaining a vacuum presented a persistent, highly complex chemical challenge. Even when a massive diffusion pump successfully removed all the free atmospheric air from a glass envelope, the internal metal components of the tube, the stamped nickel plates, the fine molybdenum wire grids, and the glowing tungsten filaments harbored massive quantities of occluded gases, primarily nitrogen, carbon monoxide, and hydrogen, trapped deep within their microscopic metallic crystalline structures. To extract these stubbornly trapped gases, manufacturers had to subject the vacuum tubes to extreme, punishing thermal processing during the pumping stage. The entire glass envelope was baked in a high-temperature oven to boil off microscopic layers of water vapor adhering to the glass, while the internal metal components were simultaneously heated to blinding incandescence using high-frequency radio induction coils placed outside the glass. Molybdenum parts required intense heating to 1760 degrees, while the tungsten filaments were flashed at staggering temperatures up to 2300 C to forcefully release their trapped internal gases so the diffusion pump could continually draw them away. However, even the most rigorous, high-temperature pumping and baking protocols could not achieve the absolutely perfect, permanent vacuum required for long-term tube reliability in consumer radios. Over months of use, tiny amounts of gas would inevitably seep out of the metals or glass, poisoning the vacuum and destroying the tube's ability to emit electrons. To solve this critical longevity problem, manufacturers turned to chemistry, relying on chemical scavengers known as getters. Getters are highly reactive alkaline earth or transition metals, such as pure barium, magnesium, zirconium, or phosphorus, which possess a violent, strong chemical affinity for free gases. During the very final stage of vacuum tube assembly, just before the glass envelope was melted shut and permanently sealed off from the vacuum pump, a small metal cup or a wire loop containing the raw getter material was intensely heated by an external radio frequency induction coil. This intense, localized heat caused the getter material to instantly vaporize or flash, rapidly filling the inside of the tube with a cloud of highly reactive metal vapor. The hot vapor reacted instantaneously with any residual oxygen, nitrogen, or carbon dioxide floating in the void, forming solid, inert chemical compounds that condensed onto the cooler inner surface of the glass bulb. This action created the distinctive, beautiful mirror-like silver coating seen at the top of vintage vacuum tubes. This metallic getter mirror was not merely cosmetic. It continued to act as a silent, continuous chemical vacuum pump throughout the entire operating life of the tube. Gaeders operated via two primary chemical mechanisms: the corrosion type, typified by barium, where the resulting chemical oxide film remained structurally porous, allowing new stray gas molecules to continuously penetrate the surface and react with the pure barium underneath; and the solution type, typified by zirconium, which could absorb up to 40 times its own physical volume of oxygen and nitrogen directly into its solid metallic matrix at elevated operating temperatures. The masterful combination of high-speed diffusion pumping with advanced reactive Gaeder chemistry completely finalized the industrialization of the vacuum tube, producing reliable components by the millions and setting the stage for the unprecedented technological demands of global warfare. The outbreak of the Second World War triggered a hyper-accelerated, desperate evolution in electronics, demanding the production of highly reliable vacuum tubes at a scale, durability, and complexity previously unimaginable. Major American and British manufacturing firms, including RCA, Sylvania, Raytheon, and Western Electric, rapidly expanded their factory operations, transforming civilian radio production lines into vast military arsenals manned heavily by newly trained female workforces. The insatiable wartime demand for specialized, ruggedized vacuum tubes catalyzed the rapid development of entirely new scientific disciplines, specifically high-power microwave radar, miniaturized smart munitions, large-scale atomic isotope separation, and the dawn of digital computing. The radar war, Klystrons, Magnetrons, and TR switches. At the onset of the conflict in 1939, both the Allied and Axis powers possessed highly functional radar, or radio detection and ranging systems, utilizing lower-frequency VHF and HF radio waves to bounce signals off metallic aircraft and determine their range. The famous British chain-home early warning system successfully utilized these lower frequencies to detect incoming German bomber squadrons during the Battle of Britain, saving the nation. However, the long physical wavelengths of these early radio signals required massive static antenna masts over 100 meters high to focus the beam, rendering the equipment entirely impossible to mount on moving aircraft or small naval ships. The overwhelming tactical necessity for airborne radar in night fighters and submarine hunting aircraft drove the rapid development of vacuum tubes capable of generating high-power microwaves. Because microwaves possess very short wavelengths, they allow for the use of small, highly directional dish-shaped antennas. In 1937, the American Varian brothers had invented the Klystron, a linear beam vacuum tube that successfully amplified high radio frequencies into the microwave range. But early Klystron models severely lacked the immense burst power required for long-range pulse radar. The critical war-winning leap occurred in February 1940 at the University of Birmingham, where British physicists John Randall and Harry Boot developed the resonant cavity magnetron. The magnetron was a radically different, highly complex type of vacuum tube. A central, heated cylindrical cathode was surrounded by a massive, solid copper anode block, bored with precise, keyhole-shaped resonant cavities. The entire copper assembly was placed in an incredibly powerful magnetic field. When high voltage was applied, the electrons emitted by the cathode were forced by the magnetic field into tight, spiraling circular orbits around the central space. As this dense cloud of spinning electrons swept past the openings of the tuned copper cavities, it induced violent, resonant microwave oscillations, much like blowing air forcefully across the open mouth of a glass bottle to produce a loud tone. The magnetron was a device of staggering power, capable of producing microwave pulses in the multi-kilowatt range, an unimaginable leap in performance. Shared eagerly with the United States during the highly secretive 1940 Tizard mission, the cavity magnetron became the absolute workhorse of Allied radar, fundamentally shifting the technological balance of the war and dooming the Axis submarine fleets. However, the sheer devastating power of the magnetron presented a severe, seemingly impossible engineering paradox. Radar systems operate by transmitting a massive, blinding pulse of radio energy and then immediately listening for an incredibly faint returning echo bouncing off a distant target. Because weight and physical space were strictly limited in aircraft, the radar system had to use the exact same dish antenna for both transmitting the blast and receiving the whisper. The receiving circuitry relied on delicate silicon point contact rectifiers, early, highly fragile crystal diodes that were exceptionally sensitive. If the megawatt-level transmit pulse from the magnetron fed backwards into the receiver circuitry, it would instantly vaporize the fragile crystal detector, leaving the radar blind. To solve this critical switching problem at the speed of light, engineers developed TR switches. These were specialized gas-filled discharge tubes placed directly in the hollow metal waveguide piping between the transmitter, the antenna, and the receiver. Unlike high-vacuum thermionic valves, TR tubes, such as the 721A, 724B, and 1B23, intentionally contained a specific reservoir of low-pressure gas. When the magnetron fired its massive pulse, the incredibly high-intensity electromagnetic field instantly ionized the gas within the TR tube, violently stripping electrons from the gas atoms and transforming the gas into a highly conductive plasma. This glowing plasma effectively acted as a solid, impermeable metal wall, instantly short-circuiting the path to the receiver and reflecting the transmitted pulse safely out to the antenna. The exact microsecond the transmission ceased, the plasma rapidly recombined into a neutral, transparent gas, instantly opening the pathway for the incredibly faint returning echo to pass safely through the tube and reach the sensitive crystal detector. The successful mass production of highly reliable TR tubes enabled precision microwave radar targeting, transforming warfare forever. The proximity fuse, miniaturization under extreme force. While radar searched the skies, another profound, highly secretive application of vacuum technology sought to revolutionize the lethality of anti-aircraft artillery. Before World War II, anti-aircraft shells relied almost entirely on mechanical time fuses. This required artillery gunners to accurately calculate the exact altitude, speed, and time of flight to detonate the shell precisely near a fast-moving enemy aircraft. Even minor calculation errors resulted in the shell exploding harmlessly in empty space, wasting millions of rounds of ammunition. The U.S. Navy and a team of brilliant civilian scientists at the Johns Hopkins University Applied Physics Laboratory, operating under the highly classified designation Section T, sought to solve this by creating a smart shell containing its own miniature onboard radar system. This device, officially known as the VT or Variable Time or Proximity Fuse, required embedding a complete continuous wave radio transmitter and receiver directly inside the cramped nose cone of an artillery shell. The engineering challenges were seemingly insurmountable. The electronic brain of the fuse required vacuum tubes to generate and detect the radio signals, but standard glass vacuum tubes were exceedingly fragile, prone to shattering if dropped on the floor. To function, these tubes had to survive the catastrophic explosive shock of being fired from a 5-inch naval gun. The initial blast subjected the fuse to acceleration forces up to 22,000 times the force of gravity, 22,000 Gs, immediately followed by the intense centrifugal forces of the shell spinning at thousands of revolutions per minute to maintain ballistic stability in flight. Section T researchers initially experimented with ruggedized metal envelope tubes, but ultimately succeeded by radically miniaturizing glass vacuum tubes, reducing them to the size of a pencil eraser, making the internal components shorter and less prone to bending. To protect the delicate internal wire grids and glass-to-metal seals from the massive launch forces, the tiny tubes were suspended in blocks of plastic and heavily potted in shock-absorbing wax. Powered by specialized, highly dangerous reserve batteries whose liquid electrolytes were violently released and activated by the spin of the shell, the proximity fuse transmitted a continuous radio signal as it flew through the air. When the shell approached a solid target, the radio waves reflected off the aircraft and interacted with the transmitted signal, creating an oscillating Doppler shift in the tiny receiver. Once this shifted signal reached a critical amplitude, indicating the target was dangerously close, the fuse's specialized Hadron tube triggered the detonator, destroying the target precisely within its maximum lethal blast radius. Regarded by military historians as a technological innovation on par with radar and the atomic bomb, the proximity fuse was guarded under extreme secrecy, kept away from land battles for years to prevent the Germans from recovering a dud and reverse engineering the technology. Over 100 American companies were mobilized to manufacture the components, resulting in the massive production of over 20 million fuses. The ruggedized, sub-miniaturized vacuum tubes developed for this program not only devastated Axis aircraft and famously protected London from waves of V-1 flying bombs, but also firmly established the physical and manufacturing foundations for the post-war sub-miniature electronics, hearing aid, and aerospace industries. The Manhattan Project, Gaseous Diffusion, and Mass Spectrometry. The most secretive, expensive, and monumental endeavor of the Second World War, the Manhattan Project, also pushed vacuum engineering to unprecedented, almost unimaginable industrial extremes. To construct an atomic weapon, the United States needed to physically separate the highly fissile uranium-235 isotope from the vastly more abundant but non-fissile uranium-238 isotope. Because the two isotopes are chemically identical, standard chemical extraction methods were entirely useless. The separation had to rely entirely on the minuscule physical difference in their atomic mass. A U-235 atom is slightly lighter than a U-238 atom. The primary method chosen to achieve this was gaseous diffusion, which capitalized on the fundamental principle that lighter molecules of a gas will effuse through a microscopic porous barrier slightly faster than heavier ones. To facilitate this complex physical process, solid uranium metal was converted into uranium hexafluoride, UF6 gas. The choice of UF6 was highly deliberate. Because the element fluorine possesses only one natural isotope, any minute difference in the total weight of the UF6 gas molecules was guaranteed to be entirely due to the difference between the U-235 and U-238 atoms. Pumping UF6 was an absolute engineering nightmare. The gas is incredibly corrosive, highly reactive with moisture, and solidifies rapidly if the temperature fluctuates even slightly. The K-25 gaseous diffusion plant, built secretly at Oak Ridge, Tennessee, was designed to house the massive cascade of billions of microscopic diffusion barriers necessary to slowly enrich the uranium. Constructed between 1943 and 1945 at a staggering cost of $500 million, the massive U-shaped K-25 building measured half a mile long, covered over 5 million square feet of floor space, and briefly held the title of the largest building under a single roof in the world. The K-25 plant was in essence the largest and most complex continuous high-vacuum envelope ever constructed in human history. The system comprised thousands of miles of tightly sealed piping, massive custom-built compressors, and millions of diffusion barriers. For the delicate enrichment cascade to function, the entire massive system had to be completely devoid of atmospheric air and moisture. Even a microscopic pinhole leak in the miles of piping would introduce atmospheric water vapor, which would violently react with the uranium hexafluoride gas to form a solid powdery compound called uranyl fluoride. This powder would instantly plug the billions of microscopic pores in the delicate diffusion barriers, completely ruining the enrichment process and shutting down the plant. Standard industrial leak detection methods of the 1940s were woefully inadequate for a vacuum system of this colossal scale and sensitivity. The ingenious solution came from Alfred Neer, a brilliant physicist at the University of Minnesota, who had previously utilized his custom-built sector mass spectrometers to physically isolate U-235 and prove that it was indeed the fissile isotope of uranium. A mass spectrometer operates by ionizing a sample of gas in a high vacuum, accelerating the charged ions through a curved magnetic field and separating them based on their mass-to-charge ratio. Because lighter ions bend more sharply in a magnetic field than heavier ions, the device can sort atoms by weight. Neer, working closely with the Kelix Corporation, brilliantly adapted his fragile, highly complex laboratory mass spectrometers into robust, highly portable industrial leak detectors. By tuning the mass spectrometer to exclusively detect the light, highly mobile, and completely inert gas helium, technicians could precisely pinpoint microscopic leaks in the massive K-25 infrastructure. A vacuum pump would evacuate a large section of piping connected to Neer's mass spectrometer, while a technician slowly sprayed a fine jet of helium gas over the exterior welds, joints, and valves. If even a single molecule of helium penetrated a microscopic pinhole in the metal, it would instantly be sucked into the vacuum, swept into the mass spectrometer, bent by the magnetic field, and registered as a loud squeal by the spectrometer's vacuum tube audio amplifiers. This brilliant marriage of high vacuum technology, mass spectrometry, and heavy industrial fabrication ensured the successful continuous operation of the K-25 plant, ultimately yielding the highly enriched uranium that fueled the little boy atomic bomb. The dawn of digital computing. ENIAC. While the Manhattan Project utilized vacuum technology to tame the immense energy of the atom, the United States Army utilized it to conquer overwhelming mathematical complexity, an effort that led directly to the birth of the modern computer. During the war, the rapid, massive deployment of new artillery pieces required the generation of vast, highly accurate mathematical firing tables. These tables, which allowed soldiers to aim their guns accurately, had to take into account dozens of variables, including projectile mass, wind speed, air density, and propellant temperature, requiring the solution of highly complex non-linear differential equations. At the time, this excruciating labor was performed almost entirely by human computers, predominantly brilliant female mathematicians operating clattering mechanical desk calculators, a process that was grindingly slow and entirely incapable of keeping pace with the rapid demands of the battlefield. In 1943, visionary physicist John W. Mauchly and brilliant electronic engineer J. Presper Eckert at the University of Pennsylvania's Moore School of Electrical Engineering secured a highly classified Army contract to build a massive mathematical robot capable of calculating artillery trajectories at electronic speeds. The result of their tireless work was the Electronic Numerical Integrator and Computer, ENIAC, widely and rightly recognized today as the world's first programmable general-purpose electronic digital computer. Unlike all previous mechanical calculators, which relied on slowly moving physical gears, cogs, and electromechanical relays operating in sluggish milliseconds, the ENIAC replaced physical mechanical movement with the entirely frictionless, lightning-fast flow of electrons. The fundamental beating heart of the machine was the vacuum tube. However, Eckert and Mauchly repurposed the vacuum tube from its traditional role as a radio amplifier or audio detector into a high-speed, binary electronic switch capable of changing states, on or off, in mere microseconds. Because electrons have virtually no physical mass, they do not suffer from mechanical inertia. They can be started and stopped instantly by manipulating the voltage on the grid of the vacuum tube. ENIAC was an absolute engineering behemoth, It weighed 30 tons, occupied 1,500 square feet of floor space, and contained 70,000 resistors, 10,000 capacitors, 1,500 mechanical relays, and an astounding 17,468 vacuum tubes, primarily common off-the-shelf octal base radio types like the 6SN7 for logic flip-flops and 6L7s and 6L6s for driving pulses through the massive cable assemblies. The transition from mechanical computation to electronic switching brought an unprecedented world-altering increase in speed. ENIAC could calculate a complete 60-second artillery trajectory in just 30 seconds, a staggering 2,400 times faster than a highly trained human mathematician with a desk calculator. However, this raw speed came at a colossal operational and environmental cost. The massive array of glowing filaments consumed 160 kilowatts of electricity, generating immense, suffocating heat that frequently pushed the ambient room temperature to a blistering 120 F. To prevent the machine from melting its own solder joints, it necessitated the continuous, deafening operation of two massive 20-horsepower industrial blowers just to keep the ambient temperature survivable. Local Philadelphia legends famously, if perhaps apocryphally, claimed that the city's streetlights dimmed whenever the massive machine was powered on. The greatest, most persistent challenge facing the ENIAC engineering team was reliability. Skeptics and rival engineers originally argued vehemently that the machine would never function for more than a few seconds, mathematically proving that the inherent failure rate of the sheer number of vacuum tubes would guarantee constant downtime. With 17,468 vacuum tubes operating at a rapid clock speed of 100,000 pulses per second, the ENIAC was subjected to an incomprehensible 1.8 billion chances for a catastrophic failure every single second it operated. A single burned-out filament, a shorted grid, a failing getter, or a drifted resistor could instantly ruin a complex calculation, turning a mathematically correct ascending artillery shell trajectory into a plummeting, lethal error. Initially, the ENIAC suffered severe downtimes, with vacuum tubes failing as frequently as every 48 hours. To combat this, Eckert and his engineering team implemented extreme military-grade maintenance routines. Through rigorous statistical life testing of the tubes, they discovered a critical truth. Vacuum tubes suffered the most severe thermal and mechanical shock during the power-up and power-down phases. Constantly turning the filaments on and off caused the internal metal elements to rapidly expand and contract, leading to metal fatigue and broken filaments. The radical solution was to simply leave the ENIAC powered on continuously, 24 hours a day, maintaining thermal equilibrium and vastly extending the lifespans of the components. Furthermore, Eckert instituted incredibly strict derating design standards across the entire machine. Every single electronic component, from the 6SN7 flip-flop tubes to the thousands of standard carbon resistors, was intentionally operated at voltages and currents significantly below their manufacturer's maximum ratings, severely minimizing thermal stress and maximizing longevity. Maintenance crews conducted grueling, unusual preventative regimens. They famously waited until nightfall to turn off the room lights and hunt through the towering cabinets for dim heaters, tubes whose glowing filaments were slowly fading, indicating they were about to fail and required immediate preemptive replacement. They also employed aggressive culling methods, allegedly dropping batches of fresh vacuum tubes on the hard floor. Those that survived the severe mechanical shock without their internal elements shorting out were deemed physically robust enough to be installed in the computer. Through these exhaustive, relentless methods, the mean time between failures was pushed to remarkable lengths, ensuring the machine's operational viability and proving that massive electronic systems were practical. Equally revolutionary and tragically overlooked by history for decades was the human element required to actually operate this massive vacuum tube architecture. ENIAC was not a stored program computer in the modern sense. It possessed no operating system, no keyboard, and no software coding language. When a new differential equation or physics problem was required, the machine had to be completely physically rewired to create the exact circuit path needed for that specific math problem. This monumental, exhausting task fell to a team of 6 brilliant female mathematicians, including Jean Bartik and Frances Hulberton, who had originally been heard as human computers. Given only the vast, highly complex paper schematics of the machine's electronic circuitry, these women effectively invented the discipline of computer programming from scratch. They translated complex mathematical algorithms into physical routing paths, manipulating thousands of heavy black cables, plugging them into endless arrays of sockets, and meticulously setting over 6,000 manual rotary dials to direct the exact flow of electronic pulses through the labyrinth of vacuum tubes. A single programming change could take up to 2 days of grueling physical labor, crawling inside the machine's infrastructure just to set up a calculation that the machine would complete in seconds. Their pioneering, brilliant work on the ENIAC proved conclusively that vacuum tubes could handle massive, complex logic algorithms flawlessly. Recognizing the severe physical limitations of having to manually rewire the machine, the ENIAC team, heavily influenced by John von Neumann, soon developed the concepts of storing instructions in memory alongside the data. The success of ENIAC and its vacuum tube logic directly catalyzed the development of commercial computing systems like UNIVAC, setting the definitive stage for the software and hardware revolution that would define the rest of the 20th century. The post-World War II scientific imperative and the Cold War context. In the immediate aftermath of World War II, the acceleration of atomic research, the proliferation of microwave electronics, and the development of ballistic missile technologies demanded environments entirely free of atmospheric interference. The space race, which grew out of the nuclear arms race between the United States and the Soviet Union, fundamentally shifted the priorities of national engineering programs. On October 4, 1957, the Soviet Union successfully launched Sputnik 1, the first artificial satellite, followed merely a month later by Sputnik 2 carrying the dog Laika. This triggered a massive mobilization of Western scientific resources. To develop satellites, advanced rocketry, and eventually human spaceflight, engineers needed to subject materials to the extreme airless conditions of the cosmos while still on the ground. Simultaneously, the foundational components of the modern electronic age were being forged. Early nuclear reactors and advanced microwave electron tubes, such as the Klystrons used in early particle accelerators and high-power radar systems, required pristine internal vacuums. Any residual gas molecules inside a klystron would become ionized by the high-voltage electron beams, leading to catastrophic arcing, beam scattering, and the rapid degradation of the component. The traditional oil diffusion pumps that had served early 20th century industry were fraught with severe limitations. Chief among these was the issue of backstreaming, a process wherein the hydrocarbon or silicone oils used as the pumping fluid would vaporize and migrate backward into the vacuum chamber. This backstreaming coated sensitive internal components with a microscopic layer of organic contamination, rendering the vacuum entirely unsuitable for sensitive atomic or optical research. As the tolerance for surface contamination shrank to the atomic level, the scientific community realized that achieving the UHV regime required completely reimagining the physical mechanisms of gas extraction. The kinetic revolution, turbomolecular pumps. The desperate demand for a clean, oil-free high vacuum led to one of the most significant mechanical breakthroughs in vacuum engineering, the turbomolecular pump. Developed and patented in 1958 by Dr. Willy Becher at Pfeiffer Vacuum, the turbomolecular pump fundamentally altered the landscape of vacuum generation by utilizing the kinetic theory of gases. Prior to Becher's invention, the most common methods relied either on the entrapment of gases in fluids or the mechanical sweeping of large volumes of air. Becher's design, however, physically resembled the interior of an advanced aircraft jet engine. The turbomolecular pump consists of a multi-stage rotor featuring dozens of angled, bladed discs that spin at extraordinarily high velocities, often ranging between 30,000 and 90,000 revolutions per minute. Interposed mirror-invertedly between these rapidly rotating rotor discs are stationary bladed stator discs. The pump operates within the molecular flow regime, where gas molecules move independently rather than as a continuous fluid. When a wandering gas molecule randomly enters the inlet of the pump, it is struck by the angled blades of the rapidly spinning rotor. This physical collision transfers kinetic energy to the molecule, imparting a strong directional momentum that drives it deeper into the pump assembly. As the molecule is battered down through successive stages of alternating rotors and stators, it is compressed and pushed toward the exhaust port, where a traditional backing pump reduces the pressure further and exhausts the gas to the atmosphere. Becher's invention was revolutionary because it entirely bypassed the need for vaporized sealing oils, thereby eliminating hydrocarbon backstreaming and enabling the reliable, continuous generation of vacuum levels down to the extreme high vacuum range of 10 to the negative 11 millibars. The success of the turbomolecular pump was immediate and transformative. Its relative ease of operation, long mechanical life, and absolute cleanliness quickly made it the dominant technology for creating high vacuum environments, largely replacing the oil diffusion pump. Over the subsequent decades, Pfeiffer Vacuum and other manufacturers continued to pioneer advancements in this technology, eventually introducing magnetically levitated rotors that eliminated physical bearing contact entirely, further reducing vibration and wear for highly sensitive analytical applications. Ionization and capture, the Sputter ion pump. While turbomolecular pumps excelled at continuously moving gases out of a chamber, engineers focusing on the longevity and purity of sealed systems, such as microwave electron tubes, required an entirely different approach, the capture pump. In 1957, researchers Robert L. Jebsen, Lewis D. Hall, and John C. Helmer at Varian Associates filed a patent for the first practical sputter ion pump, later commercialized under the name VAC ion. Varian Associates, co-founded in 1948 by Russell and Sigurd Varian, the inventors of the Klystron tube, initially developed this pump as an appendage device designed to maintain UHV conditions in microwave power tubes after they had been sealed. The conceptual foundation of the ion pump was rooted in observations made in 1937 by Franz Michel Penning, who noticed that cold cathode gauges exhibited a slight but measurable pumping effect. While Penning's early devices were too slow for commercial viability, the Varian research team under Jebsen's direction optimized the design into a highly efficient gas capture mechanism. The optimized ion pump utilized a unique architecture consisting of honeycomb-shaped cylindrical anodes situated between two flat cathodes made of highly reactive getter materials, predominantly titanium. The mechanics of the ion pump rely on the complex interplay of high electrical voltages and strong magnetic fields. Electrons are introduced into the anode cells, where the magnetic field forces them into long, tightly wound helical trajectories. This dramatically increases the path length of the electrons, vastly amplifying the probability that they will collide with a residual gas molecule wandering through the chamber. When a collision occurs, the gas molecule is ionized. The newly formed positively charged ion is immediately accelerated by the strong electric field and slammed into the titanium cathode with tremendous kinetic energy. This violent impact causes titanium atoms to be sputtered or physically ejected from the solid cathode array, coating the internal surfaces of the pump with a continuously refreshed layer of highly reactive metal. Active atmospheric gases, such as oxygen, nitrogen, and carbon dioxide, chemically react with this fresh titanium film to form stable, solid titanium compounds, effectively removing them from the vacuum space permanently. Meanwhile, lighter gases, like hydrogen, are implanted directly into the cathode lattice and diffuse into the bulk metal, while inert noble gases, which do not react chemically, are physically buried beneath the continuously accumulating layers of sputtered titanium. By 1959, Varian had successfully scaled this technology from small appendage pumps to massive units capable of pumping thousands of liters per second, developing the necessary peripheral components such as high-voltage feed-throughs, massive magnets, and specialized ultra-high vacuum flanges. Because they contain absolutely no moving parts and require no lubricating oils, ion pumps are inherently vibration-free, perfectly clean, and capable of operating continuously for years, making them an indispensable technology for maintaining deep UHV conditions in everything from particle accelerators to electron microscopes. Thermodynamics and the void, cryopumping. As industrial and scientific applications demanded even higher pumping speeds, particularly for problematic gases like water vapor and hydrogen, the field of extreme thermodynamics intersected with vacuum science to produce the modern cryopump. A cryopump operates on the principle of extreme thermal reduction, utilizing a closed-loop helium refrigeration unit, often called a cryocooler or cold head, to cool internal pumping arrays to temperatures near absolute zero, typically below 20 Kelvin. The underlying mechanics of a cryopump rely on the saturated vapor pressure of gases. As ambient temperatures drop, the vapor pressure of a surrounding gas plummets accordingly. When residual gas molecules enter the pump and collide with the cryogenically cooled surfaces, they lose their kinetic energy instantly and undergo a phase change, condensing from a gas directly into a solid state. To achieve this, commercial helium-supplied cryocoolers operate in two distinct stages. The first stage cools an outer radiation shield and a gas inlet baffle to approximately 80 Kelvin, well below the temperature of liquid nitrogen. This outer baffle pre-cools incoming gases and completely freezes out massive volumes of water vapor, acting much like a thermos flask to reflect ambient heat away from the deepest recesses of the pump. The second, inner stage, utilizes a lower cooling capacity but achieves temperatures below 20 Kelvin. At this extreme temperature, almost all remaining atmospheric gases, including nitrogen, oxygen, and argon, freeze solid. Highly volatile, low-mass gases like hydrogen, helium, and neon, which resist freezing even at these temperatures, are captured via physiabsorption within highly porous materials, such as activated charcoal that are bonded directly to the coldest inner arrays. Compared to turbomolecular pumps, cryopumps offer exceptionally high pumping speeds and can achieve lower ultimate pressures much faster for a given inlet diameter. However, because they are capture pumps, they retain all the frozen gas within their housing. Consequently, cryopumps cannot be exposed to atmospheric pressure while cold, necessitating the use of heavy isolation valves, and they require periodic regeneration routines where the pump is warmed and the accumulated layers of frozen gas are exhausted to a safe external system. Today, massive multi-stage cryopumps are critical for maintaining millikelvin environments in quantum computing racks and ensuring absolute purity in commercial solid-state battery deposition lines. The semiconductor paradox: complexity dictates absolute emptiness. The modern world is vertically integrated upon the foundation of the transistor, and the relentless pursuit of Moore's law, the observation that the number of transistors on a microchip doubles roughly every 2 years, has driven the global economy for over half a century. Today, a single leading-edge microchip contains tens of billions of nanoscale electronic switches connected by roughly 60 miles of microscopic copper wiring, all packed into a form factor the size of a coin. The technology trajectory from hand-soldered discrete components to the precise atomic-level layering of integrated circuits has provided the computational power necessary for the Internet, artificial intelligence, and global telecommunications. However, this trajectory of exponential miniaturization has given rise to a profound technological paradox. The creation of the most intricate, complex, and densely packed physical structures ever engineered by humanity requires an environment that is as close to absolute nothingness as physically possible. Vacuum technology is no longer an auxiliary laboratory tool. It is the stripped, uncompromising, and highly expensive prerequisite for all contemporary semiconductor manufacturing. The extreme sensitivity of nanoscale fabrication means that a single microscopic dust particle, a stray water molecule, or the presence of reactive atmospheric gases can result in catastrophic defects, destroying the functionality of an entire silicon die. As the industry transitions from the 5 nanometer node down to the 2 nanometer and 1 nanometer eras, incorporating revolutionary transistor architectures like gate-all-around and complementary field effect transistors, the margin for error has vanished. Because transistors are shrinking to dimensions where quantum tunneling becomes a significant physical hurdle, ensuring the absolute purity of the materials deposited and the precise energy of the ions implanted demands complete isolation from the Earth's atmosphere. Thus, almost all critical fabrication steps, from chemical vapor deposition and plasma etching to advanced lithography and ion implantation, must be executed within a stringent, rigorously controlled, ultra-high vacuum. The alchemy of thin films, CVD and ALD. The foundation of all semiconductor manufacturing lies in the sequential, precise deposition of incredibly thin films of conductive, semiconductive, and insulating materials onto a pristine silicon wafer. CVD and its far more precise subclass, atomic layer deposition, or ALD, are the primary mechanisms for achieving this structural alchemy. These processes involve introducing specialized gaseous chemical precursors into a reaction chamber, where they undergo complex thermal or plasma-assisted chemical reactions to form a solid, uniform thin film on the substrate surface. Because many of the most advanced chemical precursors utilized in modern fabrication exist as liquids at room temperature, highly advanced liquid source vaporization techniques and direct liquid injection, or DLI, systems must be employed to phase change these chemicals into a gas with exceptionally stable concentration and chemical stoichiometry. To facilitate these gas phase reactions without unwanted atmospheric interference, oxidation, or spontaneous combustion, the processing chambers must be continuously evacuated to primary vacuum levels, typically operating in the range of 1/10 to 5 millibars. ALD represents the extreme limit of this deposition science. Unlike traditional CVD, ALD deposits materials just one atomic layer at a time in a sequential, self-limiting manner. A single reaction cycle requires pulsing a precursor gas, allowing it to react with the surface, and then completely purging the chamber before pulsing the second reactant. This highly repetitive process places immense mechanical stress on the vacuum infrastructure. In high-volume manufacturing environments, dry roughing pumps must possess enormous volumetric capacities, often ranging from 1,800 to 4,500 cubic meters per hour, to swiftly and entirely evacuate the precursors during the brief purge steps. thereby ensuring high throughput and preventing premature mixing of chemicals that could cause particulate fallout. Furthermore, these pumps face severe chemical challenges. The unreacted precursors and gaseous byproducts evacuated from the chamber are frequently highly corrosive, highly condensable, or capable of precipitating into solid powders directly within the mechanical pump elements, posing a constant threat of catastrophic equipment failure. The extreme ultraviolet lithography bottleneck. As the semiconductor industry pushes beyond the physical limitations of earlier nodes, traditional deep ultraviolet lithography, which operates at atmospheric pressure, utilizing light with a wavelength of 193 nanometers, has reached its absolute diffraction limits. It is physically impossible to draw the microscopic lines required for modern interconnected copper wiring schemes and gate-all-around transistors using such broad wavelengths. To resolve these incredibly small features, the entire industry has universally adopted extreme ultraviolet lithography, an enormously complex technology currently monopolized by the Dutch company ASML. EUV lithography utilizes light with a highly specific wavelength of exactly 13.5 nanometers to etch intricate circuit patterns onto photoresist-coated silicon wafers. However, the use of EUV radiation introduces a staggering and unprecedented engineering complication. Light at the 13.5 nanometer wavelength is highly energetic and is immediately and totally absorbed by any physical matter, including standard atmospheric air. Consequently, the entire lithographic process, the generation of the light source, its reflection through complex multi-layer optical columns, the shrinking of the reticle pattern, and its final projection onto the wafer, must occur within a massive, stringently controlled ultra-high vacuum. The generation of the EUV light itself is an extraordinarily violent process that pushes the boundaries of applied physics. Within the EUV source chamber, a high-power carbon dioxide laser fires dual pulses at microscopic, fast-moving droplets of liquid tin 50,000 times every single second. These high-energy laser impacts instantly vaporize the tin, creating a superheated plasma that emits the desired 13.5 nanometer radiation. A massive, highly polished, and incredibly precise collector mirror is positioned nearby to gather this emitted light and direct it into the optical column. However, this violent plasma generation process inherently creates a dense cloud of highly destructive tin debris, high-energy ions, and neutral particles that threaten to coat the surrounding surfaces. If even a microscopic layer of tin accumulates on the collector mirror, its reflectivity degrades instantly and severely, drastically reducing the power of the light reaching the wafer and crippling the manufacturing throughput of the machine. This mirror degradation presents one of the most significant barriers to cost-effective high-volume manufacturing, driving up maintenance costs and reducing equipment availability. To solve this critical contamination issue, vacuum engineers deploy a paradoxical countermeasure. They intentionally inject a continuous, massive flow of hydrogen gas directly into the ultra-high vacuum source chamber. The hydrogen molecules physically collide with and slow down the explosive tin debris. More importantly, hydrogen radicals chemically react with any deposited tin on the mirror surfaces to form stannane gas, or SNH4, which can then be safely pumped away by the vacuum system. This creates a massive logistical challenge. The primary dry pumps attached to the source chamber must possess the highest hydrogen pumping capacity on the market, continuously evacuating enormous volumes of the gas to maintain the delicate pressure balance required for plasma stability while simultaneously clearing the stannane byproducts. Meanwhile, adjacent connected chambers, such as the scanner chamber housing the delicate multi-layer mirrors and the robotic wafer handler operating with a positioning accuracy of 25 micrometers, must be maintained at pristine UHV pressures using extensive arrays of high-capacity turbomolecular pumps. The financial cost of maintaining these intricate voids is unprecedented in the history of industrial manufacturing. Developing EUV technology required over 2 decades of research, and the resulting equipment ranks among the most complex machinery ever built by human hands, with a single EUV system containing more than 100,000 highly specialized components. The cost of a single advanced EUV lithography tool routinely exceeds $30 to $40 million. The reliability of the vacuum system within these tools is paramount. Any contamination of the vacuum environment by residual hydrocarbons can cause rapid carbon growth on the optical surfaces, necessitating incredibly expensive downtime and maintenance that severely impacts the chipmaker's return on investment. Because a modern semiconductor gigafab requires dozens of these EUV tools working in tandem with hundreds of deposition, etching, and ion implantation chambers, the capital expenditure required to build a single leading-edge fabrication facility easily surpasses $10 billion, driven in massive part by the sheer cost of building, sealing, and maintaining the vacuum infrastructure. The elimination of oil. The dry pump revolution. The transition of semiconductor manufacturing to total vacuum reliance would have been fundamentally impossible without addressing the fatal flaw of traditional rotary vane and oil diffusion pumps, the pervasive threat of oil contamination. In the late 1970s and early 1980s, the increasing complexity of integrated circuits rendered any trace of hydrocarbon backstreaming from pumping fluids completely unacceptable. A single molecule of oil migrating back into an etching chamber could destroy an entire batch of highly valuable wafers. The definitive solution to this problem arrived in 1980 when Henry Wycliffe, serving as the chief engineer at Edwards Vacuum, successfully patented the first viable dry or oil-free vacuum pump, designed specifically for harsh industrial use. Despite facing initial skepticism from colleagues who believed the industry would never abandon fluid-sealed pumps, Wycliffe persisted. The essence of his revolutionary invention utilized a unique multi-stage mechanical configuration, combining roots and claw mechanisms that could aggressively compress and exhaust gases without the need for sealing fluids or lubricating oils residing anywhere within the swept volume of the pump. The dry pump revolutionized semiconductor fabrication, allowing for continuous, exceptionally clean vacuum generation. Over the subsequent decades, as chip manufacturing processes introduced increasingly toxic, reactive, and solid-forming chemistries, dry pump technology underwent rapid and continuous evolution. Modern iterations, such as the Edwards IXH series, have moved far beyond the simple evacuation of air. These advanced machines are heavily engineered to feature advanced thermal management profiles and proprietary gas barrier technologies that provide massive resistance to the highly corrosive byproducts generated by modern ALD and multi-layer etching processes. Furthermore, because modern deposition and etching chemistries often generate significant volumes of solid byproducts that can instantly seize a rapidly spinning mechanical pump, modern dry pumps are designed with extraordinary powder handling capabilities. By carefully regulating and profiling the temperature across the different compression stages of the pump, engineers can prevent the internal condensation and subsequent plating of solid materials within the pump mechanism, vastly extending the mean time between maintenance, eliminating the need for routine overhauls, and maximizing the operational uptime of the entire fabrication facility. The logistics of the void, particle dynamics, and purity piping. The sheer scale of vacuum deployment in a modern semiconductor gigafab is difficult to fully comprehend. A single facility requires the synchronized operation of thousands of advanced dry vacuum pumps, turbomolecular pumps, and cryogenic pumps. These pumps are connected to the process tools via an incredibly intricate, multi-billion-dollar infrastructure of high-purity stainless steel, specialized plastic, and copper piping systems designed for the pristine delivery of process chemicals, ultra-pure water management, and massive vacuum transport. As semiconductor manufacturing rapidly expands globally, with nations like Taiwan, South Korea, China, and the United States investing hundreds of billions of dollars to secure technological sovereignty, the demand for ultra-high purity specialty piping tailored for pristine environments continues to skyrocket. Furthermore, moving the finished, highly sensitive wafers between facilities requires a vast logistical chain of vacuum-sealed semiconductor trays designed to prevent moisture intrusion, electrostatic discharge, and particulate contamination during global transit. Within the vacuum systems themselves, engineers face the constant, maddening threat of microscopic contamination. Paradoxically, the very act of generating a vacuum can inadvertently create the exact particulate contamination it is designed to prevent. Extensive research into aerosol behavior within vacuum systems has revealed a critical phenomenon known as turbulent nucleation. During the initial rough pumping cycle of a chamber, the rapid expansion and subsequent adiabatic cooling of the resident gas can cause any residual moisture inside the chamber to instantly condense and nucleate around incredibly fine, otherwise harmless microscopic particles. If the pump-down sequence is too aggressive, the resulting atmospheric turbulence severely agitates these newly formed aerosol particles, swirling them through the chamber and depositing them directly onto the pristine wafer surface. To combat this, the industry employs complex, highly controlled, and staged pump-down sequences. Variable frequency drives gently lower the pressure at controlled rates to prevent moisture nucleation before engaging the high-speed, high-vacuum turbomolecular pumps. Additionally, engineers have discovered that in a high-vacuum environment, particles fall rapidly due to the force of gravity, devoid of the air currents that would normally keep them suspended. By placing silicon wafers in a face-down configuration during certain vacuum processes, the wafers can effectively self-shield their critical front faces from falling particulates, demonstrating the extreme lengths to which engineers must go to mitigate contamination. The cost of emptiness, ecological footprints, and energy consumption. At the macroscopic level, the energy demanded to maintain absolute emptiness across the global semiconductor industry is staggering and increasingly problematic. Semiconductor fabrication is a phenomenally utility-intensive operation, consuming massive amounts of water, emitting complex greenhouse gases, and demanding vast reserves of electrical power. It is estimated that the continuous operation of vacuum pumps alone accounts for up to 25% of the total energy consumption of a semiconductor manufacturing facility. Analyzing the global landscape, the integrated device manufacturing sector consumes an estimated 160 terawatt-hours of electricity annually, generating nearly 75 million tons of carbon dioxide equivalent in Scope 2 emissions, derived largely from power generation. If the industry continues its aggressive expansion without intervention, these emissions could increase up to 8-fold by the end of the decade, directly conflicting with global climate goals and sustainability frameworks. As the industry aggressively pushes towards the sub-2 nanometer nodes, the demand for higher pumping speeds, lower base pressures, and the safe management of increasingly toxic and complex plasma chemistries is surging. In response to growing environmental regulations, restrictive F-gas regulations, and the sheer operational costs of energy, the industrial vacuum equipment market has pivoted heavily towards the development of green vacuum technology. Major equipment manufacturers are prioritizing the development of low-energy dry pumps, employing completely redesigned, energy-efficient root mechanisms that can reduce electrical input power by up to 60% compared to legacy models, without sacrificing harsh process capability. Furthermore, these modern pumps integrate advanced idle or green modes that automatically communicate with the process tool, slowing down pump rotational speeds to conserve massive amounts of energy during the brief periods when the reaction chamber is inactive or transitioning between wafers. To manage this at a facility scale, chip makers are increasingly relying on data-driven approaches, utilizing artificial intelligence, machine learning algorithms, and dense networks of IoT sensors deployed across the fab. These advanced analytics platforms monitor real-time energy usage patterns across thousands of individual vacuum pumps, identifying inefficiencies, predicting maintenance needs, and optimizing the synchronized operation of the entire vacuum infrastructure to aggressively reduce the fab's overall carbon footprint without ever compromising the pristine, ultra-clean environments required for high-yield semiconductor production. Big science and aerospace. While the global semiconductor industry relies on the orchestrated operation of millions of relatively small, localized vacuum chambers, the realms of fundamental high-energy physics, astrophysics, and aerospace engineering require vacuum environments of unprecedented volumetric and geographical scale. These massive scientific instruments push the absolute limits of mechanical structural integrity, thermodynamic management, and materials science. Particle accelerators, the architecture of high-energy physics. To probe the fundamental, indivisible constituents of matter and understand the forces that govern the universe, physicists must accelerate subatomic particles to velocities approaching the speed of light before forcing them into violent collisions. These complex experiments require exceptionally long, completely unbroken trajectories, entirely free of wandering gas molecules. If an accelerated proton were to collide with a stray molecule of atmospheric oxygen or nitrogen, the resulting impact would severely degrade the beam data, unpredictable scattering, and the generation of massive amounts of unwanted, dangerous background radiation, ruining the experimental data. The absolute pinnacle of this vacuum engineering is the Large Hadron Collider, operated by CERN, situated beneath the border of France and Switzerland. The LHC relies on one of the largest and most intricately complex operational vacuum architectures in human existence, essentially comprising 3 completely distinct vacuum systems, spanning an astonishing 104 kilometers of total piping. The most critical of these are the twin beam pipes, stretching 54 kilometers in total, through which the counter-rotating high-energy proton beams travel. To ensure a flawless, collision-free path for the particles, the pressure within these pipes is driven down and strictly maintained between 10 to the negative 11th and 10 to the negative 12th millibars, creating an artificial void that is as highly rarefied as the desolate surface of the moon. Achieving and maintaining this extreme vacuum across such vast subterranean distances requires a multi-pronged, highly specialized technological approach. In the 48 kilometers of the LHC's curved arc sections, the massive superconducting magnets and the beam pipes running through them are cooled to extreme cryogenic temperatures of 1.9 Kelvin using thousands of liters of superfluid helium. At these incredibly low temperatures, the physical walls of the beam pipe themselves act as an enormous continuous cryopump. Any residual gas molecules striking the ultra-cold walls instantly lose their kinetic energy, condense, and are trapped indefinitely via cryosorption, successfully maintaining the UHV conditions over vast lengths without the need for active mechanical pumping mechanisms spaced along the arcs. However, the 6-kilometer straight sections of the collider, which house the massive particle detectors, beam control electronics, and experiment insertion regions, must operate at room temperature and therefore cannot rely on cryogenic condensation to maintain the vacuum. To solve this, CERN developed a highly specialized Gaede coating, a proprietary non-evaporable alloy consisting of titanium, zirconium, and vanadium. The interior surfaces of these room-temperature beam pipes are completely coated with this advanced material. When heated during the initial commissioning phase, the alloy activates and becomes highly chemically reactive, acting as a sponge that permanently absorbs residual active molecules. Because Gaede materials operate purely on chemical bonding, they cannot capture inert noble gases or methane. Consequently, an array of 780 massive ion pumps is deployed continuously along these straight sections, specifically to capture and bury these non-reactive residual gases. Constructing this massive, perfectly leak-tight infrastructure required over 250,000 precision-welded joints and 18,000 highly specialized vacuum seals, all of which are continuously monitored by a vast distributed array of Pirani, Penning, and Bayard-Alpert ionization gauges to detect even the microscopic ingress of air. Gravitational wave observatories, listening to the void. The detection of gravitational waves, infinitesimal ripples in the fabric of space-time, caused by the most violent and cataclysmic cosmic events in the universe, such as the distant merging of black holes or neutron stars, requires measurement precision that defies ordinary comprehension. To detect these waves, scientists must measure a change in distance on the order of 10 to the negative 19 meters, an oscillation roughly 10,000 times smaller than the width of a single atomic nucleus. The Laser Interferometer Gravitational Wave Observatory, or LIGO, achieves this impossible precision by splitting and bouncing highly stable, perfectly tuned laser beams between heavy, meticulously suspended test masses over a massive 4-kilometer distance. To prevent the delicate laser light from being scattered, refracted, or absorbed by wandering atmospheric gases, and to absolutely isolate the delicately suspended $2 million silica test mass mirrors from acoustic vibrations and thermal fluctuations, the entire 4-kilometer beam path must be enclosed within an ultra-high vacuum. LIGO's vacuum system encompasses an astonishing 10,000 cubic meters of volume, making it the third largest continuous vacuum chamber in the world, surpassed only by the LHC and massive aerospace testing facilities. The internal pressure is relentlessly maintained at 10 to the negative 9 torr, effectively reducing the internal atmosphere to 1/trillionth of standard sea level pressure, leaving only about 10 million molecules per cubic centimeter. The structural and civil engineering required to build and maintain this void is immense. The beam tubes, measuring 1.2 meters in diameter, are constructed from 3 mm thick spiral-welded 304L stainless steel ribbons. This specific steel alloy was chosen for its exceedingly low carbon content and its absolute resistance to corrosion, particularly at the thousands of welded seams. Because the Earth's atmosphere exerts over 10,300 kilograms of pressure per square meter of surface area, resulting in approximately 150 million kilograms of crushing atmospheric force pressing down on each 4-kilometer tube, heavy external stiffener rings had to be meticulously welded along the entire length of the segments to provide structural integrity and prevent the thin steel tubes from imploding violently. Achieving the initial deep vacuum required an epic undertaking. Massive arrays of turbopumps ran continuously for 40 days to evacuate the bulk of the atmosphere from the tubes. However, simply removing the air is insufficient for UHV. The steel itself acts as a microscopic sponge, holding vast reserves of water vapor and elemental hydrogen trapped during the smelting process. To expel these deeply embedded molecules, the entire 4-kilometer length of the tubes had to be heavily insulated and electrically heated to between 150 and 170 degrees Celsius for 30 consecutive days, a massive, unprecedented bakeout process. Once the target vacuum was achieved in the late 1990s, It has been maintained continuously for over 2 decades by sophisticated arrays of ion pumps to capture outgassing metals and liquid nitrogen cryopumps deployed specifically to freeze out rogue, stubbornly bouncing water molecules. Looking to the future of astrophysics, next-generation gravitational wave observatories, such as the proposed European Einstein Telescope and the United States Cosmic Explorer, plan to scale this vacuum technology dramatically. These future facilities propose triangular or L-shaped vacuum arms, ranging from 40, 120 to even 160 kilometers in length. Because the cost of the vacuum system scales linearly with the length of the interferometer arms, the sheer volume of the vacuum infrastructure will represent the second highest capital cost of the entire scientific endeavor, prompting unprecedented collaborations with CERN to leverage decades of particle accelerator vacuum expertise to design cheaper, more efficient nested tube and titanium sublimation pumping solutions. Aerospace and cosmic simulation. Before deploying multi-million-dollar satellites, deep space probes, or delicate Mars rovers into the unforgiving vacuum of space, aerospace engineers must rigorously simulate the severe thermal, acoustic, and barometric conditions of orbit to ensure complete hardware survivability. This testing requires the construction of massive thermal vacuum chambers. The absolute pinnacle of this engineering capability is the NASA Space Power Facility, located at the Glenn Research Center in Sandusky, Ohio. Originally constructed in 1969 to perform nuclear testing for advanced deep space missions, the SPF remains the world's largest single vacuum chamber, boasting an internal volume of 22,653 cubic meters, or roughly 800,000 cubic feet. Unlike the incredibly long, narrow tubes of LIGO or the LHC, the SPF is a colossal, cavernous cylinder measuring 30.5 meters in diameter and standing 37.2 meters high. Uniquely, the primary vacuum chamber is constructed entirely of aluminum rather than standard stainless steel. Because a massive hollow aluminum shell of that unprecedented size would risk immediate structural failure and collapse under the crushing weight of atmospheric pressure when evacuated, the entire aluminum chamber is enclosed by an equally massive concrete containment building. During operation, a complex multi-stage roughing system consisting of rotary lobed blowers reduces the pressure of the annular space between the outer concrete wall and the inner aluminum chamber down to 20 torr. This severely reduces the pressure differential acting on the inner walls, safely preventing the aluminum chamber from imploding as it is subsequently pumped down to a high vacuum of 2 × 10⁻⁶ torr. To achieve this massive evacuation in under 8 hours, the facility utilizes 5 massive turbomolecular pumps and 10 large cryopumps, providing a staggering total pumping speed of 500,000 liters per second. Once evacuated, the facility provides a massive empty arena where engineers can subject full-scale spacecraft, rocket fairings, and deployable solar sails to brutal environmental extremes. Using a variable geometry cryogenic cold shroud utilizing recirculating gaseous and liquid nitrogen, and massive arrays of quartz heat lamps and carbon lamps, the facility can rapidly cycle the internal environment from a freezing -195°C up to a blistering 60°C, perfectly replicating the harsh, unfiltered solar radiation and the freezing darkness of the cosmic void. The material barrier, permeability, desorption, and outgassing. The ultimate limitation in creating a perfect, absolute vacuum is not constrained by the capability of modern mechanical pumps, but rather by the fundamental, unavoidable physical nature of solid matter itself. No containment vessel is perfectly impermeable, and no surface is perfectly clean. When a chamber is evacuated, The severe pressure differential forces gases that are chemically dissolved within the metallic structure of the chamber's walls to slowly diffuse to the surface and desorb into the void, a persistent phenomenon known as outgassing. In the UVH and extreme high vacuum regimes, the dominant outgassing burdens are water vapor, which stubbornly adheres to metal surfaces via strong hydrogen bonding, and elemental hydrogen, which is introduced directly into the steel matrix during the high-temperature smelting and manufacturing process. The selection and treatment of materials are therefore the most critical, foundational factors in vacuum engineering. Mild steel and brass, while structurally sound and easy to machine, are virtually useless for UHV applications, exhibiting incredibly high outgassing rates in the realm of 10 to the -6 torr-liters per square centimeter. Aluminum performs significantly better, hovering around 7 times 10 to the -9th, but its susceptibility to surface imperfections, lower hardness, and higher gas permeability can pose extreme challenges for achieving and sustaining deep, long-term vacuum. Stainless steel, particularly the 304L, 316L, and 316LN alloys, remains the undisputed gold standard for vacuum construction due to its exceptionally dense crystalline structure, high strength, and absolute resistance to atmospheric corrosion. However, to reach pressures below 10 to the -11th millibars, standard stainless steel must be rigorously and aggressively heat-treated. Beyond the standard in situ bakeout processes performed at 150 to 300 degrees Celsius, the most advanced chambers are often subjected to a specialized vacuum fire process. During vacuum firing, the steel components are heated to an extreme 950 degrees Celsius for 24 hours, while held under a separate high vacuum environment before they are ever installed. This extreme thermal excursion physically expands the metal lattice and violently drives the deeply embedded hydrogen atoms out of the metal matrix permanently. Extensive comparative studies demonstrate that these vacuum-fired alloys, designated as 316L-XHV, alongside pure ASTM Grade II titanium, exhibit specific hydrogen outgassing rates below 1 × 10 to the -11 Pascal liters per second per square centimeter. This represents an incredible improvement, suppressing outgassing by at least a factor of 100 compared to standard untreated 304L steel. Yet despite these exhaustive, highly expensive material treatments, a continuous, albeit minuscule, stream of atomic desorption persists indefinitely, ensuring that the chamber can never be entirely, fundamentally emptied of matter. The quantum plenum, zero-point energy, and the Casimir effect. Even if engineers could somehow construct a perfectly impermeable containment vessel, cool its entire structure down to absolute zero to halt all thermal vibration, and successfully extract every single atom of residual gas, modern theoretical physics dictates that a perfect vacuum, a true philosophical state of absolute nothingness, is a fundamental mathematical impossibility. According to the foundational tenets of quantum mechanics and quantum field theory, the universe does not contain empty space. Rather, the vacuum is a highly dynamic, seething medium comprised of continuous, fluctuating matter fields and force fields. The Heisenberg uncertainty principle, a cornerstone of quantum mechanics, strictly prevents any quantum system, including the electromagnetic field occupying a vacuum, from resting in an absolute zero energy state. If the energy of the field were perfectly zero, both its exact value and its exact rate of change would be simultaneously known, completely violating the fundamental laws of quantum uncertainty. Therefore, the vacuum inherently retains a baseline minimum amount of fluctuating energy known universally as zero-point energy, or ZPE. This zero-point energy manifests continuously as a chaotic, boiling sea of virtual particles. pairs of matter and antimatter, such as electrons and positrons, that spontaneously pop into existence from the void, exist for an infinitesimal, unobservable fraction of a second and mutually annihilate one another before they can violate the conservation of energy. While these quantum fluctuations seem entirely theoretical and mathematical, they exert measurable, macroscopic mechanical forces on physical objects, definitively proving that the void possesses inherent thermodynamic and mechanical properties. The most famous and striking demonstration of this phenomenon is the Casimir effect, predicted theoretically by Dutch physicist Hendrik Casimir in 1948 while researching colloidal solutions at Phillips Laboratories. Casimir calculated that if two perfectly flat, uncharged, highly reflective metallic plates are placed parallel and exceedingly close to each other in a perfect vacuum, they will be mysteriously and powerfully pushed together by the void itself. This attraction occurs because the incredibly narrow space between the two plates restricts the allowable wavelengths of the virtual particles that can pop into existence between them. Because longer wavelengths are geometrically excluded from forming in the gap, there are inherently more virtual particles colliding with the outside surfaces of the plates than colliding between them, creating a differential pressure generated entirely by the quantum vacuum fluctuations. While this force is entirely imperceptible at macroscopic human scales, generating roughly 10 to the -7 newtons of attraction for two 1 square centimeter mirrors separated by a single micrometer, roughly half the weight of a tiny droplet of water, it scales violently and inversely as distances decrease. At a separation of just 10 nanometers, the Casimir effect generates an inward pressure equivalent to one full Earth atmosphere pushing the plates together. As the global semiconductor industry pushes its manufacturing deeper into the single nanometer regime, and as engineers attempt to design microscopic nano-electromechanical systems, or NEMS, for future medical and computational technologies, the vacuum ceases to be an inert absence of matter and instead becomes an active, sticky, and highly dynamic medium that physically interferes with moving parts. The reality of quantum vacuum fluctuations and the resulting inescapable Casimir forces represent the ultimate hard physical boundary of emptiness. They prove definitively that the philosophical concept of a true, absolute void is fundamentally forbidden by the very laws of nature, transforming the vacuum from a stage of emptiness into a vibrant, vibrating cosmos of infinite possibility. The concept of the vacuum has traversed a profound epistemological and technological journey, evolving from a philosophical impossibility into the most highly engineered environment on Earth. In the 19th century, the commercialization of the incandescent light bulb by Thomas Edison relied entirely on the application of the Sprengel pump, which efficiently evacuated glass globes to unprecedented levels, allowing the carbon filament to glow brilliantly without rapid oxidation. This initial commercialization of the vacuum paved the way for subsequent leaps in extraction efficiency, such as the invention of the diffusion pump by pioneers like Wolfgang Gaede and Irving Langmuir in the 1910s, which remained the industrial standard for high vacuum generation long before the advent of the kinetic turbomolecular technologies detailed in previous sections. Furthermore, the profound impact of the void was irreversibly cemented during the Second World War and its immediate aftermath through the proliferation of vacuum tubes. As noted in our historical context, the cavity magnetron, a highly specialized vacuum tube, was instrumental in generating the precise microwaves necessary for Allied radar systems, fundamentally altering the course of global conflict. Simultaneously, the dawn of the digital computing age was entirely dependent on this precise vacuum technology, most famously embodied by the ENIAC computer, which utilized over 18,000 vacuum tubes to achieve what were then unprecedented calculation speeds. The mechanical breakthroughs of the mid-20th century, such as the kinetic extraction mechanisms of the turbomolecular pump, the chemical capture capabilities of the Sputter ion pump, and the extreme thermodynamics of modern cryopumping, bypassed the severe limitations of early fluid-sealed systems. These innovations made pristine, reliable UHV environments an industrial reality. Today, this architecture of emptiness is the uncompromising foundation of the global economy, enabling the intricate atomic alchemy of advanced semiconductor deposition and the staggering complexity of extreme UV lithography, while driving innovations in dry pumping to reduce the industry's massive ecological footprint. Moreover, the ability to scale these voids has pushed the boundaries of human knowledge, allowing physicists to probe the fundamental particles of the universe at the Large Hadron Collider and listen to the infinitesimal ripples of spacetime at LIGO. Yet, as engineers push toward the ultimate limits of pressure, they are met with the insurmountable barriers of material outgassing and the boiling dynamic sea of quantum vacuum fluctuations governed by the Casimir effect. Ultimately, the perfect void remains a physical impossibility, but our relentless pursuit of it has transformed the vacuum from a simple absence of matter into the active, indispensable substrate of the modern world.